Hello, discrete math fans. Let's give a couple of examples of sequences that are defined recursively. For instance, let's write out the first 5 terms of the sequence that's defined by a sub n equals a sub n minus 1 plus 3 to the n, and that recurrence relation is good as long as n is bigger than or equal to 1, and then we have to define a sub 0, and we're just going to say a sub 0 is 1. Now we're given the first term, so we'll just compute the next 4 terms using the recurrence relation. So now to figure out what a1 is, we'll just plug in n equals 1 into the recurrence relation. So that's how we get a1 is equal to a naught plus 3 to the first, and so we end up with 4. And we can keep doing that until we have 5 terms. We started with a0, and then we get a1, a2, a3, and a4. Notice that that's 5 terms. Even though we're stopping at a4, there's 5 terms because we started at a0. Let's try another one. Let's write out now the first 8 terms of the sequence that's defined by this recurrence relation. A sub n is equal to a sub n minus 1 plus a sub n minus 2. That recurrence relation is good as long as n is bigger than or equal to 2. And then we're going to give 2 initial conditions. A sub 0 equals 0, a sub 1 is equal to 1. Now you don't need to know terms like this, but this particular recurrence relation is what would be called a second order recurrence relation because it defines values of a sub n based on terms in the sequence that run 2 before a sub n. The one we started with initially was a first order recurrence relation. Now we're given a sub 0 equals 0 and a sub 1 is equal to 1, so that's 2 of the terms. So we need to compute 6 more terms. And we just use the recurrence. a2 is equal to a1 plus a0, so that's 1 plus 0 is equal to 1. a3 is 1 plus 1 equals 2. So each time we compute a term in the sequence, we're adding the 2 before it. And of course, you should recognize this. This is the world-famous Fibonacci sequence, which we've talked about before, and we'll discuss again in the future. Okay, that's all for now.